Originally, Java had no preprocessor as in C or macroprocessor as in assembly language. When you looked at a line of Java code, you could tell exactly what it was doing. With the newer versions of Java, by including special preprocessing commands called generics, you are able to instruct the Java compiler to do some special invisible checking. The action of generics is sort of like casting that works at compile time. Here is the definition of a simple wrapper class not using generics. This class is able to contain one object. It can hold an object of any class. This is an example of putting a string object into the wrapper and returning it. The type of object is not specified by the declaration of the method in the class, so it is necessary to cast the return object. Without specifying the type of object being stored, the wrapper is capable to hold anything. You could make a more restrictive wrapper and limit its contents like this. This is the same as the previous example, except this time the wrapper is more particular about what it accepts and what it returns. The object passed to it and returned from it must be a string. In this example, not only will the wrapper prohibit all but one kind of object from being placed in it, but it's no longer necessary to cast a returned value. It's known ahead of time exactly what is to be returned. Something similar can be done with generics this way. This is the same thing again, but in this case, the Java compiler has done some hidden type checking. The wrapper class is defined with a less than and greater than sign surrounding the variable that is to become the type of the object. You can use any symbol you like to specify the class name variable, but commonly single-letter uppercase symbols are used. Whatever symbol you choose will be used throughout the class. Whenever you need to create an object from the class, you include the name of the type you want between the less than and greater than signs. When you put objects in and take objects out, it's just as if you had edited the class names into the source, except there is no source that represents the rules that are applied when the code is generated. The casting of the types is present in the generated code, but none of that information shows up in the source. Here's a rough idea of how it works. There is nothing you can do with generics that you can't do with your text editor. One way to look at generics is that it checks on the correctness of casting in the compiler instead of waiting until runtime. Here's how it works. The class is compiled into a regular class file, except the generic annotations are present, so the macro can be expanded when you use it. Under normal circumstances, a class file has the same name as the class it contains, but in this case, any type parameters that you have defined as part of the class name are left off the file. That is sort of correct because no information about the actual type is included in the code itself. Remember, the actual type information doesn't come about until later when you use the new command to create an object from the class definition. Code is compiled that will work equally well with any type of object, just like in our first example. When an object is created from the class, it is created using exactly the same code as would be created if none of the generic information had been included. However, the generic type information from the instantiation is stored along with the newly created object. When the compiler generates the code for such things as method calls and variable accesses, it does the type checking then and there. This is very much like type checking that's done in casting, but the check for casting is done at runtime. Generic type checking is done at compile time. This is really the only advantage of generic type checking, the fact that it's done at compile time instead of later at runtime. However, and this is important so you can understand what you can do and can't do, once the code to access the class members is generated, the type information is discarded. The absence of this information has some important effects on object-oriented programming, as we will see in upcoming lessons. In the Java documentation, this discarding of information is referred to as type erasure. And if you decide you want to use generics, you need to be aware of the limitations that this causes. In the next lesson, I will explain the generic naming conventions and some things about how it works with constructors and methods. Simple classes aren't the only parameter types you can specify for generics. There is a naming convention that is often adhered to. It isn't required by the language, it's only a convention. The first thing you'll notice about the convention is that all the names are made of single uppercase letters. You've already seen this one. In the previous example, it was used as the macro symbol representing a class with objects stored in a wrapper. This is for elements. This is the one you can see used a lot in the classes that are included as part of the Java standard library. You can tell by this category that the naming convention is more about how things are used than what they really are. In a later lesson, I will be showing you how to use more than one parameter. For multiples, the convention is to use letters that don't have another definition. But in truth, you can use anything you want. It just makes the code a little easier to decipher if you follow the conventions. You can use generics to apply to only a single method. It doesn't matter whether or not the method is inside a class that is also defined as a generic. In this example, the only thing generic in the class is this one method. Notice how the method is defined. The generic type has to be defined somewhere, so it can be just stuck in front of the definition of the method. It has nothing to do with the method type or its return value. It's just the place where you define the type variable name. When you call this variable, you can call it with any object type. Now, these two methods are actually the same. The only difference is that the parameter to the genType method becomes whatever type is passed to it, and the objType method remains a method that accepts anything. It's a subtle difference, and the code that's generated by the two is the same. You can create an instance of a generic class so that it will accept anything. This object will accept anything that is a subclass of object, and every Java class is a subclass of object, so it will accept anything. As you can see, you need to cast the returned object. The executable code generated by this code is the same as it would be if the original class were not defined as a generic. This may seem like sort of the long way around to do nothing. However, I have needed to do this. Several of the standard Java classes have been modified and now they require generics, and I have been able to use this technique to compile some of my older code with the newer compiler. I'll have some more to say about this in the later lesson on gotchas. In the next lessons on generics, I will show you how to define generic classes that will work with families of classes. You can use object-oriented programming techniques in a limited way when working with generics, but to do so requires that you use some new syntax. The extends keyword in this context limits which classes can be used in the declaration to those that are a subclass of number. The integer class is a subclass of number, so it can be used. Also, the double class is a subclass of number, so it can be used. But that's not all extends means in this context. In this example, the type isn't limited to a subclass. The type must implement the interface named eventListener. The syntax of the code between the less than and greater than signs of the generic definition is not the same as it is in the rest of Java. With the addition of generics, Java no longer has a context-free grammar. Keywords and operators have different meanings depending on where they are used. In this context, the keyword extends means that the chosen class is limited to either a subclass of the named class or that it implements the named interface. In this example, the classes JTable and UndoManager can be both used because they both implement the Event Listener interface. You can include both class names and interface names as the limiting requirements on the same type variable. In this example, the type used must be both a subclass of image and implement the interface transparency. The buffered image class is both of these things, so it can be used. You can have as many interfaces as you wish in the list. Including more than one class in the list would be pointless because of the single inheritance of Java. The ampersand character has a different meaning in this context than it does in normal Java expressions. Normally, a comma is used as the separator in lists, but in this context, the ANDing operator is used instead. If you want to use inheritance to construct your objects, you might want to avoid generics. They don't work as you might expect them to. Take this declaration. You might wonder how it falls in the class hierarchy of superclasses and subclasses. Well, it doesn't. It's very much of a standalone item. The stash class has a superclass. You can define it as extending another class, or it will default to object being its superclass, but the number class hierarchy cannot come into play here. You might think this is a subclass, but it's not. Remember the earlier lesson about discarded information? The very thing that you will need to inherit the information about the number is the very thing that's thrown away. There is no way to build a subclass of stash either, because no stash class definition exists without the generic part being added to it. To create a superclass and subclass relationship, you could create the superclass this way. Then you could create a subclass to hold whatever types of number objects you like. It would only be a matter of overriding a few functions to do the more stringent type checking. You could easily make a class for any kind of number. They could both be made to be subclasses easily enough, and the type checking would be done at compile time, so you would have all the advantages that you get from generics. One more lesson on generics coming up: generic wildcards and the nesting of generic names. Earlier, you saw how to use the question mark character to represent any class, and you saw how to use the extends keyword to limit the class to a specific subclass and implementers of specific interfaces. Now I want to show you the results of using them together. This is the same stash class that we looked at earlier, but this one is used a bit differently. This is an attempt to allow generics to use polymorphism, but it only partially works. Notice this reference for a stash object named numberStash is declared with a question mark for the type, but it also binds the unknown type to be something that extends the number class. This is the instantiation of an object that meets the requirement, but we have to start with it in a reference to its own type named integerStash, because we couldn't write to it if we were to put it into numberStash. It's because of that lack of inheritance thing I talked about in the previous lesson. Anyway, with the stash object being a reference of the right type, integer objects can be added to it freely. Now that we're not going to write to it anymore, we can copy the address of the integer stash object into the generalized number stash object. We can't write to it when it's in this form, but we can read from it as long as we are not specific about the type of number that we read. Every number object has a toString method, and it can be called. Here is almost the same thing done again, this time with a double, which is also a subclass of number. The only difference is that the returned object is cast to its class instead of being left as its superclass. So far, we have looked at the lower bounds definition, which has the form of using the extends keyword like this. This means that the objects must be a number object or an object of one of its subclasses, such as integer, double, short, byte, and so on. But it is also possible to have upper bounds like this. This form limits the choices to the number class or the object class, which is its only superclass. Here's an example of using two type declarations in the generic definition. You can include as many as you like this way. Just separate the names with commas. Here are two simple wrappers. The pair class can contain two objects and the stash class can contain one. Here's an example of the two of them used together. This is the declaration of a reference named SP that can contain the address of a stash object, and the stash object can contain a pair object. The pair object can contain a string object and a long object. This statement constructs the actual object. These final two statements build the string object and long object and put them in a pair wrapper, and then puts the pair wrapper in the stash wrapper. To demonstrate that it works, these final two statements pull the objects out of the wrappers and display them. By the way, this is an annotation. I'll be talking more about them later. The purpose of this annotation is to suppress a warning message about something being unchecked. If you use generics much, you'll often get these false warning messages. They usually don't mean anything. The class compiles just fine, but they are a nuisance. There are lots of different types of warning messages, and you can find that you may want to suppress a lot of them. When this program runs, it looks like this. That covers the basics of generics. Beginning with the next lesson, we'll be looking into Java's collection framework, and several of them use generics.